Hi, welcome to Domain-Specific Languages with me, Cliff Click. Okay, what is a DSL? It's a specialized tool for a specialized problem. And, as opposed to a general purpose language. So these kind of be broken down in a couple different ways. One way to look at them is external versus internal, where an external language is one where there's a dedicated parser and execution. Sometimes these are not Turing complete, such as Markdown or PML as a markup language. And then internal ones where you're using language X's parser. So you're writing at a subset of X, but are helping you write language Y. So for instance, a query DSL is going to help you write SQL for queries, but you're writing your main application in C# or Java. Or Elm as a way to write reactive coding for JavaScript and HTML. Or maybe a C++ operator overloading for doing bulk array math or doing some sort of physics equations at scale. And the other way to break them out is what do we do with the IR? So programs are just hard to work with directly, and that's why we use IRs at all. And the most obvious IR is none. And this would be direct code generation. So very simple, no optimization, sort of a see, do kind of thing. But once you do the code gen, instead of interpreting, you're maybe 2x to 10x faster. And because they're simple, they can be written in a day or two. The next IR, obvious one, is an abstract syntax tree, which I say just enough to get the job done. They're really powerful. A lot of people use them for a lot of things. You can do some obvious, easy optimizations. You can do some fairly complicated ones. They miss out on the ultimate set of things, and they miss out on certain kinds of heavyweight transformations that are key in some domains. So people still do heavyweight IRs in DSLs. In particular, anytime you're doing, say, loop fusion or stream fusion, becomes difficult to do it at the AST level in a general purpose kind of way. All right, so let's look at some examples here. So here's the easiest language on the planet, an external, no IR, forth. A 1970s typeless stack-based language. It has a REPL, it has a JIT. The syntax is literally only white spaces, tokens, and not tokens. That's it. The interpreter just looks up a token. If it finds the token, it's going to execute the address that came with it. And if it doesn't find a token, it must be a number. And otherwise, it's a syntax error. When you look at the thing in the middle, that's an increment X. It says call X, which pushes the address of variable X on the stack. Then convert the address to the value for X, push a 1, add it, push the address on the stack again, store it. Pretty simple. Compiling it is almost the same thing. And it's in fact, the same interpreter is used for compiling. You just put a colon down, the next token in, that's your function name. After that, you follow your standard function execution. Instead of executing, you gather the tokens up, put them in a buffer till you hit a semicolon. That's the end of your definition. How is that implemented under the hood? The compiler and the REPL, they're almost totally identical, except you have a pile of function addresses out of the compiler. And if you put the function addresses in a buffer, you get the top line there, the top green line there, where I just have a series of function addresses, one after another. The only exception is the number 1 has a function for a constant injected in front of it. And to execute it, you have an interpreter that loads up an address and executes it. Loads an address and executes it non-stop. That's all it does, right? Given that that's how simple the interpreter is, you can get the next fancier step here by replacing the address of a function with a call instruction, an x86 hardware call instruction, followed by that same address. Now you're directly executable just without an interpreter, and that's twice as fast at least. And then the next further step down is you can inline the bodies, because most of these function calls are extremely tiny, and you can just directly inline them without any further optimization, just a template style copy. And you get the code at the bottom, which again is about twice as fast as the code above it. Okay, let's change examples here. At some point in my life, I did the hotspot Java virtual machine, and I wrote lots and lots of complicated assembly with lots of complicated interactions with the runtime, and these standard assembly was just too dumb. I wanted some smart help, right? So I wanted to auto-emit read and write garbage collection barriers, or building GC mapping tables, or memory barriers for volatiles, or I had to do alignment for self-modifying code snippets because I can't self-modify code that was spanning a cache line boundary, for instance. The complicated stuff, not your normal thing. Fine. I wrote a DSL for assembly, and the DSL is actually valid C code. So the block on the right there, that's valid C code. But it reads like assembly. And when you execute the C code, it doesn't execute that assembly. It writes that assembly code as machine code in a buffer that I can execute later. And I can do other things with that code in the buffer, like add tables with GC mapping off to the side, or put barriers in, or add no ops to do padding for whatever. Okay. Here's another one. This is command line for sort. I did this one when I was a much younger guy. And of course, the command line options on the right, you run it on and on and on. Sort has a bazillion command line options. And if you look how sort is implemented in the innermost loop of your quick sort kind of thing, there's a compare function that's using the command line arguments to describe what to compare, and it can run into the millions and billions of executions. That is completely your bottleneck on sort. So how do we make that go faster? Interpreting those options on the command line, that can be very slow when you're doing it billions of times. You take the command line arguments, and you know that the data is going to get loaded in a 2D array of structs. And the compare function is going to get called with the base of 2 different rows, which are just bunch of 4-byte things in a row where the pointers are strings or integers. And now I look at my dash K 2, 1, I want column 2 and column 1, column 2 is ints. So the first couple of lines there are going to be load 4 of an age and look comp 4 of an age. And what's the offset? 8, that's 4 bytes times column 2. And if those are equal, I fall into the next code where I load the last name as 4 bytes times column 1 and do a string compare, and I jump out. Running this code is going to be easily an order of magnitude faster than interpreting the command line every go around. In fact, I could optimize this code further doing like tail jump elimination, tail call elimination for the call return, and something fun with the load for compare for could be a subtract for, and then the end result is also valid as flags. All right, fine, whatever. All right, let's look at an abstract syntax trees now, because this is where things get a little more fancy and people do more interesting optimizations. Most languages are just built with recursive structure. They naturally break down to a tree. The ASTs are easy to read, easy to follow and debug, easy to walk with tree-based optimization passes. You do give up on sort of maximal optimization because there's some things that are not conveniently represented in a tree, like code scheduling, that you want to do a different way. But ASTs are strong enough that they're common first choice for many DSLs, and maybe the only choice, and furthermore, they only need one pass over an AST. They're pretty good. Here's an example of Kotlin where I want to do a Kotlin to SQL, where I'm going to write some Kotlin code that describes a database query, all the parts I need. I'm going to change my queries constantly as I do my business logic, and I don't want to keep recomputing my SQL. I want my SQL to be automatically computed. In fact, the results from the query return can be auto-injected back into my Kotlin structures. So I have some sort of schema here on the right that I've written in Kotlin that describes a database schema. I have a query builder in the middle. I've written one of the query selectors. We might have however many query selectors are necessary. Then I write my queries. And the query builder will convert that into a where, c.id equals 42 is SQL, gets shipped to the database, and I don't have to worry about SQL writing ever again. All right, let's look at another one here. This is Python to big data, where Python has the issue that it just tops out in scale. Say for R, a couple of these data science languages have a scale issue. And so I want to write my Python code and have an interactive feel, but I can't put the data in Python because it's terabytes. So I need to put the data somewhere else, and I want to take my Python expressions and evaluate them. And I don't want to write a Python interpreter. That's too complicated. Python's a pretty fancy language, actually, under the hood. So I'm going to do this clever hack where I overload Python operators to build an AST for expressions. So here my data science is, find the gender column, find all the zeros in the gender column, set them to Python's missing notion, which my big data side knows how to handle missing. And that changes the data science. It's different from 0. So I need to refine my operators, including array lookup and equal equals and all that kind of stuff, and replace the data, which would have been a data frame with a lot of data in it, with an AST generator, and then run that expression, build an AST. Data of square bracket gender string builds the top little tree in the top right, and the bigger expression in the middle builds the bigger expression in the middle, the bigger tree in the middle, and I can nearly arbitrary Python expressions get turned into ASTs. And it's the nearly here that saves the day because Python's too complicated. I can't do it all. I just need to do the big data bits, the bulk array bits. What do I do with this tree? Well, I walk it once and spit out a URL-friendly string. Then I URL encode it, and I ship it over the cluster. In this case, it was an H2O cluster, but it could have been TensorFlow, it could have been Spark, Databricks, whatever. You decode it, build an AST by parsing this AST-friendly string. and then evaluate it. And the evaluator has a tree now, and it has a data set that may be terabytes in size. And it begins evaluating by walking the tree and doing, bottom up standard tree walk. Bottom left corner here, I find data, that's my data set. I do a column selector off of gender. I do an equals 0, that's my first big data walk where I compare this column to 0 and put down a Boolean column. And then I do a column selector for doing an assignment operator. And then I finally replace the column back in as the last part of it. And I've done this big data expression that I wrote in Python. Okay, enough of that. Let's look at some heavyweight IRs really briefly here. These are used when you have to do sort of major optimizations. A lot of well understood, well known languages do heavyweight optimizations. Whether or not you call these DSLs or not kind of depends on your point of view. But the common theme here is that these languages have alternative dispatch rules, and the core host language won't inline for you. So you have to manually inline. Or you're looking at fusing streams and loops, because when you're walking over big data, the right level of loop size and scale and streaming will make a huge payoff, orders of magnitude speed ups. So definitely worth it. Or you have alternative concurrency models like lazy evaluation or the like, where you have to really change how things behave. So I'm not going to go into how those IRs work. That's a full compiler course. I'm going to show you a different one. Here's Elm. It lets me do reactive coding for HTML and JavaScript. And it builds an incremental DOM modification out of my Elm code. So I write in a high-level language, Elm. It's purely functional, no side effects, static strong typing using Haskell's typer. And when it's done typing, my web pages typically just work. It's pretty slick. So I have Elm-based HTML builder. So I have Elm code that is also smells like HTML that I'm using to build my HTML structures. And I have some rich Elm content that does whatever Elm does, including maps over functional things and concatenation and zipping and unzipping structures and things you might want to do with large data structures pretty reasonably, in a high-level language. Okay. What can I say about DSLs here? Well, they're a lot of fun. This was my first programming language, was Forth, and it basically was a DSL. I was writing it over the BASIC that came with my Trash 80. That was a pretty long time ago. Okay, and they can be very, very convenient, much more convenient than writing it yourself. That assembly thing I did for Hotspot, it would not have been possible to do that because there's too many bugs in the code if you had to hand manage all the complicated things. Having the assembler made a huge difference there, right? And DSLs can be simple. And simple ones are, well, they're simple. And that makes them easy to make and easy to understand and debug. And there's this continuum from simple to complicated, depending on your job. You can use a prior language parser. You can write your own. You can directly emit results, or you can build an AST or something fancier. They just make specialized jobs a whole lot easier. Thanks. Bye-bye.